I told them they should get it tattooed and it would make them cool. I'm sure you'd be the life of the party if you had a unit circle tattoo, you know, with all the angles on it and all the points. Everybody's gonna ask you, what is that? Well, I was in love once. And I got this tattoo. And then we broke up.
I was in love. It was cute. It turned out she was obtuse and it just wasn't right.
So we should actually get T-shirts. They won't forget it with all the weird things we've done. We did blood splatter analysis the other day. I actually threw ketchup around the room when they made them actually go down and learn. And I said, remember when I told you you won't remember me in 10 years? You might remember me in 10 years just for this weird thing I'm going to do. So I'm going to do the two-dimensional Laplaces equation because it's wildly important. Of course, for me, it's the steady-state solution of the heat equation. So that's where it's important for me. Again, I just point out that if you have, again, where the derivative is 0 is critical. That's a mic joke. The derivative being 0 is an important thing when you're in one dimension. It's an important thing if you're in two dimensions. It's a steady state. So if you set ut equal to 0, you get uxx plus uyy, and that is Laplace's equation. So again, this is two-dimensional, so now you can think of a sheet. There's an x dimension and there's a y dimension. And in this problem, x is going to be allowed to go to infinity. So it's going to start at 0 and go to infinity. And there's going to be, the y has height h. Think of a bar, not a rod anymore. And u of xy is where the temperature converged to in the heat equation, right? If ut is 0, you can kind of think of it as the limit. X and y are greater than 0, so I'm thinking on the top quadrant, and y is smaller than h, that's where the equation's defined. There's boundary conditions. I'm going to assume that u of x 0 is 0, and u of x h is 0. So those are these two pieces right here. So on the boundaries, the temperature is defined to be 0. Over here, I'm going to assume that u of 0y is equal to 1. And the other boundary condition is as x goes to infinity, I'm going to assume u of xy as x goes to infinity is 0. So these are all a set of boundary conditions that are imposed. So the method of solving this is called separation of variables. It seems like it's benign, but it's not, because it's much more messy. And this is probably where you used Fourier series. I'm not sure, but you might have used Fourier series here in your past. So the idea is that you're going to make an assumption that u of xy has a form. So this is what my initial professor at Georgia Tech was famous for, is guessing solutions to partial differential equations by just assuming they have some form. And so I'm going to assume that it's in the form of a product of two separate functions. One is a function of only x, and one is a function of only y. So x times y, for example, would be an example of a product like this. And once I make that assumption, I can take all the derivatives, all the partial derivatives, and pop them back into the equation. For example, uxx is the second derivative. G of y is a constant when I'm taking the derivative of with respect to x. So I get the second derivative of f times g, and uyy is f times the second derivative of g. Same deal. You know, I don't even have to go through the work for that one. Once I calculate these two guys, I substitute them back into the steady state equation, or Laplace's equation, and I get this formula. And by the way, if you want to watch this on Chris Tisdale's site, he does a very good job going through this, much slower than I'm going. So you have that, I rewrote it at the top. If you solve for these equations, you can set the f minus f of x g double prime on the right side, and you can cross multiply, and the cross multiplication gives you this funky relationship that f double prime divided by f is equal to g double prime divided by g. Now a function of f, x equals a function of y, they're both varying. That can only happen if they're both constants. So I set it equal to lambda, which I shouldn't have done because lambda indicates something to do with eigenvalues usually. So I got into trouble later because I needed the eigenvalues. But I'm going to call the eigenvalues mu. So this is the reason. You have a function of x, and it's equal to a function of y, and that's only possible if they're equal to a constant. So that's what I have right now. So the first proportion, if I cross multiply the first proportion, I get an ordinary differential equation. F double prime of x is equal to lambda f of x. The second proportion gives me a second differential equation. So I have two differential equations that theoretically I can solve. I also have these boundary conditions, and they translate. For example, u of x 0 equals 0 means if I pop it into the what I assumed that it was a product of these two functions, then I get, well, I don't want f of x to be identically 0, or else I have a trivial solution. So that means g at 0 must be equal to 0. And then I'm popping in the other boundary condition. That gives me g at h equals 0 by the same reasoning. So here's equation 2. I'm going to work with equation 2 first. I have g double prime equals minus lambda g, and I have that boundary condition. So I'm going to rewrite it in this way. This is a second order ordinary differential equation, and there's several possibilities. For example, lambda could be identically 0. If lambda was 0, what do I get from that? Well, I get that g double prime is 0, which means that g prime of y is a constant, which means that g of y is a constant y plus b. If I apply the boundary conditions, I end up with g is identically 0. So it's the trivial solution. Make sense? Case 2 is that it's less than 0. Well, in this case, I get g double prime negative g. I get mu squared is plus lambda. This is the what's called the eigenvalue equation. So you replace g double prime with mu squared and the g with a 1. If you had a g prime in that equation, you would replace it with a mu. So you'll get a characteristic equation. In Chris Tisdale's lecture, he says they're not the same eigenvalues as, they are the same eigenvalues as you remember, because I'm going to show you that on the side on the board later, but you can replace this entire thing as a matrix equation. And it turns out that the characteristic polynomial for that matrix is exactly this. So it is exactly the characteristic polynomial from a matrix. That's the same one and the same thing. So solve for mu, and we get mu is equal to plus or minus the square root of minus lambda. And minus lambda is bigger than 0 because lambda was less than 0. So the solution, the general form of the solution from a DE class, they tell you that it's a constant e to the first square root of minus lambda t plus another constant times minus square root of minus lambda t. Have you seen this before, Jimmy?
Yes.
Okay. All right, so that's just a general form of that solution. Then you pop in the eigenvalues, the initial conditions, the boundary conditions. G at 0, 0 is first, and we get a minus b from that. Pop in the second one, and unfortunately you get b is 0, which means that a is 0 too, and you're back down to the trivial solution. So you don't get anything. You don't want that too, because if g of y is identically 0, then u is identically 0, which is just the trivial solution. So you don't get anything interesting from that. The last case is lambda is bigger than 0. This is where the good stuff comes. So in this one, we do the same thing. We find the eigenvalues. I'm not going to go through that again, but this time the eigenvalues turn out to be complex. And when you have complex eigenvalues, your solution is of the form a cosine squared of lambda t plus b sine squared of lambda t. That's the general form of the solution when you have complex eigenvalues. Popping in the boundary conditions tells us that a is 0, which is pretty nice. And popping in the second boundary condition, well, I get b is 0, but I don't want that because then I get another trivial solution. But I could get sine is 0 all over the place. And that would happen when every time the square root of lambda h is equal to k times pi. Right, every multiple of pi, it's going to blot out and be 0. So what does that mean? Well, I can solve for square root of lambda. So that tells me that if lambda is k pi over h squared, quantity squared, I'm going to have a solution. A sequence of solutions, in fact. So the eigenvalues are indeed the eigenvalues as you know them, by the way. And I get a sequence of solutions for g of y. It should be really g subscript y, because I get a sequence of them. All of them work. All of them, if you substitute them back for g of y, will work. Of the form b sub k sine of k pi y divided by h. And those are different constants for every k. Woohoo, we're not done. This is a marathon. So the bk is a sequence of arbitrary constants, and the bk's are dependent on each k. So you have an infinite number of equations to solve for to get rid of that arbitrary constant. Doesn't sound fun. Now we've done 2, but we haven't touched 1 yet. So let's go back to 1. We have that f double prime is equal to lambda f. Lambda's bigger than 0. So we're going to work down the, we already know lambda's bigger than 0 because we worked down the cases, and all of the other cases gave me trivial solutions, so I'm only keeping the lambda bigger than 0. I know what happens when lambda's bigger than 0. I get a constant minus, I know what the solution's supposed to expand as. Well, now I have the other boundary conditions. Like f at 0, g of y is, g at h is supposed to be, f at 0, g of y is supposed to be 1. And the limit as x goes to infinity of f of x, g of y is equal to 0. I got those from the u at 0, comma y is equal to 1, and u of x, y goes to 0 as x goes to infinity. So those two pieces I haven't used yet. So one thing I can do is I can replace square root of lambda with this expression. And since I use subscripts for my c's, I have to put the n's at the top. That's not an exponent. And I have a nice ugly form for my u of xy in terms of a big mess. So what do I get from u of xy going to 0 as x goes to infinity? Well, as x goes to infinity, do I have 2 minuses? I don't think I should. Yeah, one of them shouldn't be minus. C2n will, C1 and this term here will go to 0, and I'll just be left with this term here. And since I don't want the bn's to be 0, that means the C2's are going to all be 0. So that's where that disappears out from. This should be a positive, not a negative here, right up here. So I get uxy, I only capture the first term. I don't get the second one because it drops out, because I want to preserve the fact that the bn's don't disappear out. I can take these two guys and absorb them as 1, and I'm going to call that little bn. So now I have a nicer looking sequence of equations. On page 173, you have the concept of superposition. That means if you have one solution and add it to another solution, the sum will be a solution too. And you can think of y, right? If you have one solution and it fits in the equation, it makes uxx plus uyy equals 0. And you have another solution and it sums up to 0. Well, when you add them, they're also going to, because taking the derivatives are linear, so it's going to sum up to 0. So the sum of all these guys, all these individual guys, are also going to, it's going to be the entire set of solutions. So that's what the formal solution looks like. What is that? That's a Fourier series. I haven't used yet u of 0y is equal to 1, so I can use that. U of 0y is that mess. That's a Fourier series indeed. And there's actually a formula to compute the b of n's using the fact that f of y is 1. It's called the Fourier coefficient. You substitute f of y is, little f of y is 1, and you can actually integrate that, or Maple can do it for you because you're lazy. And then you can make it look nicer if you want to. Like you can, leave it as a cosines n pi's in there. Or you can think of the fact that whenever n is even, you're going to get a 0. Whenever n is odd, you're going to get a 4 over n pi. And you can even clean that up further and make it look as in a nice closed form. But I got tired right here and said, okay, I'm just going to leave it like that. Now I have a form of the solution. And my Mabel was hanging on me right around then, but I wanted to just take a sum of a few of these and graph it to see what it looked like. So you can make it look nicer if you want to. And that's what I have for now. It's actually a lot, believe it or not. It's like
the fastest I've ever seen a PDE solve. The fastest you've ever learned two PDEs.
So I wanted to assign you some. I have it marked in here.